And again, if you're on the wait list, don't enter it here. Just the people who are registered. Okay? If you aren't registered, or you believe you're registered, and your name is not here, then put it on. Okay? But this is the latest that I have obtained. Okay, today, Monday, again, this is not going to be a typical lecture. This is introduction material is kind of just the idea to get a survey of different types of differential equations, and I'll probably start next week when we get down to the actual solution. Okay, that's the idea of this whole course, right? How do you solve differential equations? So we spoke on a Monday about different types of equations, ordinary versus partial. And as I had mentioned, this course will deal exclusively with ordinary differential equations, which you recall means that there can be one or more dependent variables, but only one independent variable. And that independent variable depends upon the context, right? If it's a mechanics problem like dynamics, then the independent variable usually is t, which is time. If it's something like a hanging cable, which we're going to do today, then x is the distance along the cable. Okay? So again, don't get hung up on y and x all the time. I think I mentioned this before. I've seen many students where if I write the differential equation in terms of y and x, they can solve it. And if I do like q versus t, they don't know how to do it. Okay? Y and x are just symbols. Okay? In this book, y is always the dependent variable, x is the independent. But you should get used to other symbols too. What I want to talk about today is linear versus nonlinear. I think everybody has sort of like a feeling, from their courses in mechanics about a linear versus a nonlinear problem. But of course, to do this in a mathematical setting, we have to be rigorous and define exactly what we mean that a differential equation is linear versus a nonlinear equation. Before I do that, let me just give you an example of what that you've already seen many times before. Okay? I'm going to look, some of you have already seen this before. I'm going to look at a simple pendulum. Okay? So there's a support over here, right? I'll just draw a vertical line over here, just like that. Okay? And here's the pendulum, right? And have a heavy mass m over here. Okay? And I'll pull theta in deviation from the vertical. Measure it that way. So theta equals, this line over here is just a line of, say when theta is equal to 0. So maybe I'll just draw that dotted. Just a reference, right? And the idealization over here is that it's a pendulum and that the supporting cord is massless, like a string, okay, very light, so neglect its mass, compared to the tip mass end that's on that pendulum. And what do? We basically deflect it to the right or to the left, and it's going to oscillate back and forth. You've all seen that before. Okay. Well, how do you derive the equation for that? You just use Newton's law. Okay. You use Lagrange's equations, Newton's law, and basically what you do is you take Newton's law of the F equals ma, right, and you resolve it along the tangent to this direction. Okay. And when you do that, you get the following equation for theta. This is no approximation other than the idealization of the math model. So it would be theta double dot, or second is prime, plus g over L sine theta is equal to 0. That's the differential equation governing free oscillations of this suspended pendulum mass. Okay? Theta, as you can see in the diagram, is just the deflection from the vertical. Theta positive to the right, theta negative means it's to the left. And g is the acceleration due to gravity. Okay, we incorporate it to the equation in a nonlinear fashion. Sine theta is a nonlinear function of theta, right? If you graph sine theta versus theta, you don't get a straight line, right? Basically, you know what a sine curve looks like. Okay? Can you solve that? Yes. Okay? But it's in terms of what's called elliptic functions, and the period is elliptic integral, and that's way beyond the scope of this course. Okay? Many graduate students don't even know about elliptic functions and elliptic integrals. Okay? But you know, the ancients like Euler, they always love to solve these type of problems, and there's a whole literature on these so-called elliptic functions. You can look up in Wikipedia, and they describe these nonlinear oscillation type problems. Okay? I still haven't defined carefully what a nonlinear equation is. I'm just giving you a physical feel for it. Okay? So that's basically the nonlinear equation. Okay? What's the linearized version? This is what's done in all your physics textbooks. Okay? Remember that there's a series expansion for sine theta, right? It looks like theta in radians, right? Minus theta cubed over 3 factorial plus theta to the 5 factorial, da, da, da. That's the Taylor series for sine theta, okay? And what is done in the elementary physics courses is we assume basically that theta is very small, okay? So when theta is very small, we can approximate sine theta by theta, because that's basically order theta cubed. So this is an approximation, okay? For theta small, whatever that means, and we can go into this a little later on. I have some nice MATLAB scripts that we're going to look at this equation and see when does the linear model break down and when do you need the nonlinear model. Well, for theta small, okay, sine theta is approximately equal to theta. So what's done later on, okay, is they just substitute for sine theta theta. And now you have the second of theta with respect to time plus g over L theta is equal to 0. That's the linear equation. Okay? Now, these are not the same. They're obviously quite different. This is the exact equation, which comes out to be nonlinear. And for theta small, we basically replace sine theta by theta, and therefore the governing equation becomes linear. Why is it linear? Because here you get sine theta, which is a nonlinear function of theta. Here you just have theta, which you give L theta, which is a straight line. Okay? And for theta small, sine of theta is approximately equal to. That's the sign for approximately equal to. I don't want to say equal, so you do something with tilde on there. To say it's approximately equal to theta, right? If you go into your calculator and you basically make a table of theta versus sine theta, you'll see that you start at 0.001 radians. It's pretty good. It's pretty good. And once you get to something like half a radian, it starts to deviate. Okay. Okay. This is the equation which we're going to be able to solve in a couple of weeks, okay? And it comes out that the general solution of this equation, you have to just take me on faith, is equal to C1 sine radical G over LT plus another arbitrary constant cosine radical G over LT. Again, why two arbitrary constants? The same physics that I explained on Monday, right? Imagine you do several experiments with this. Maybe some guy starts off with theta initially equal to 0.2 radians, and he lets it go from rest. Some other person starts at 0.3 radians and gives it initial velocity. And that's why the two arbitrary constants go in, so it can absorb that physical condition that initially we can have different values of theta and d theta dt. Okay. So it's basically that's a pure oscillation, the same frequency, radical G over L. And of course, if you have sine, notice that both the sine and the cosine have the same frequency. And this is how you get that famous formula for the period, right? It's 2 pi radical L over G. That's the period. And the period is the time in seconds required for this thing to go through a complete oscillation. Okay, now that's the linear model. If you would compare that with the period for the nonlinear, it's different. As a matter of fact, there's a lot of interesting things, but I can't get into them, that are different between these two models. Okay? In the linearized model, the period doesn't depend upon the amplitude. So the person who deflects it 2 radians, 0.2 radians versus 0.3 radians, they will observe, that ideal model predicts the same period for the oscillation. It comes out when you go to the nonlinear model that the period is not independent of the amplitude. Okay? The person who pulls it further away has to wait longer time for the thing to go through one oscillation. It's still periodic, but not the same period. And here the period depends upon the amplitude, here it doesn't. So there's a big difference between linear and nonlinear equations. And I'm saying the study of nonlinear differential equations is a whole subject matter in itself, and we'll touch a little upon that near the end of the course, but not really in depth. Okay. So here you have an example. Now I have to define, for our purposes in this course, what do we mean by a linear differential equation? Okay? So this is going to be basically a definition. Okay? What's going to be is very easy. It's better to say in words before I write it down. What we're going to have one independent variable, which is x, right? Let's call the dependent variable y, okay? To be general. And what a linear differential equation is, it's a relationship that connects the dependent variable y and its derivatives, okay? But it only involves powers of the dependent variable, which are and the derivative that are only linear. What do I mean by that? I'll just write down the most general equation. A sub n of x, nth derivative of y with respect to x, okay? Plus a sub n minus 1 of x, n's first derivative of y with respect to x, okay? Then it keeps going down, dot, then finally y. a1 of x dy dx, plus a naught of x times y is some function f of x. Okay? So what we see on the left-hand side, notice you have a linear combination of y, its first derivative, all the way up to the nth derivative. Okay, if it was a second-order equation, it'd just be a linear combination of y, dy dx, and y double prime. The coefficients don't have to be constants; they could be functions of x, and these guys could be anything. They could be x cubed, sine x, e dx. Okay. The important thing is that when you look at the dependent variable, you don't see anything like y squared. You don't see y dy dx, okay? It's simply a linear combination of y and all of its derivatives multiplied by functions of x that are arbitrary. And the right-hand side could be an arbitrary function of x. You know, it could be like x cubed, e dx, anything, okay? So this is basically the most general nth-order linear differential equation, okay? And basically, most of the course will be dealing with this, okay? It would be nice if you could write down just one formula for the solution of this, then the class would be over, okay? But it's not that simple, okay? And we're going to go in baby steps. First, we're going to look at first-order equations. Then we'll go to equations of order 2, constant coefficients. Okay? So this is basically your definition of a linear nth-order differential equation. Now I'm going to do something that's not in the book, but they're very useful tools, so I want you to listen carefully, okay? What happens is that you can write this equation in the following form. This is just a notation. L operating on y equals f of x. So what's going to happen is time and time again, I want to write this linear combination, and you see it took me about, it just takes time to write it all the time. So basically, the shorthand notation L on y means the following. It's not L times y, it's not a matrix times y, it's what's called a linear differential operator. And think of it as like a black box. You give me a function y of x, okay, coming in. Okay, y of x coming in. Here's the operator L, okay. Then what comes out is L on y, which is basically this thing over here, okay. Okay, so basically once you give me the operator L, you'll know all these derivatives over here. So the L on y is just the left-hand side, okay. So you give me basically these coefficients, I give a naught of x y, a1 dy dx, whatever it is, that's L on y, and the right-hand side is just f of x. Okay. And actually what's nice about this notation is that later on when you take things like linear algebra, you're going to have to find the same type of structure to it. Okay? Matter of fact, linear operators in general always of this form. Okay. So what I'm going to do now is give a rigorous definition, again, which is not in the book, of this thing being linear. So this is a definition now of a linear operator. In order for L to be a linear operator, it has to satisfy two conditions. Number one is that L operating on y1 plus y2, which are both functions of x, has has to be L operating on y1 plus L operating on y2. I'll give some examples, okay? Number two, L operating on alpha y of x is alpha L operating on y. That's basically the rigorous definition of a linear operator. In words, what does the first thing say? It says you give me two functions, y1 of x and y2 of x. I add the two together first, and I hit it with the operator L. It's the same as if I applied the operator L separately to each of the two functions and then added. And this is a scaling property. Over here, alpha is a constant. Right? And y1, y2 obviously the functions of x. Right? The second thing says you give me some scalar alpha, like 5, okay? And if I apply the operator L to the scalar times y of x, it's the same as taking L operating on y and just multiplying it by alpha. Okay? That's basically your definition of a linear operator. Okay? Okay, let me show you, for example, now that this thing, and I'll just do it for the case of 2. Okay? But it doesn't make a difference. You'll see n equals 3 is the same thing. Okay? Obviously, here I defined a linear differential equation. This is a linear operator. Okay? In order to be compatible, this equation, or this operator rather, just satisfies these two conditions. Let's show that. It's very simple. It's just a matter of, it comes out, as you'll see, is that it rests upon the fact that the derivative of the sum is the sum of the derivatives, and the derivative of a constant times a function is what? The constant times the derivative of the function. Okay. So this is the case n is equal to 2. Okay? Then L operating on y is what? It's going to be a2 of x times second derivative of y with respect to x plus a1 of x dy dx plus a naught of x times y. Right? And remember, in doing the proving that the operator is linear, you only look at the left-hand side. We don't care about the right-hand side. This is a function only of the independent variable. I don't care how complicated that is. Right? It's the basically how's the y, the